Welcome to the Explainer. Today, we're going to dig into the incredible specialized hardware that's powering so much of modern AI. It's a story that starts with a huge crisis at Google, one that led to a complete revolution in how we think about computing. So let's set the scene. The year is 2013, and Google is facing a tidal wave. The demand for AI features, stuff like voice search, was just exploding. It was growing so fast that if they kept going with the processors they were using, they would have had to literally double the number of their massive data centers. And that wasn't just crazy expensive, it's pretty much impossible. I mean, what do you do? This wasn't a problem you could just throw a little more money at or make things incrementally faster. No, this was a tear it all down and start from scratch kind of moment. This crisis forced them to completely rethink how AI computation should work, right down to the bare metal. The answer wasn't a better version of what they already had. It was to build something totally different, an application-specific integrated circuit, or ASIC. Now, that's just a fancy way of saying it's a chip designed to do one thing and do it exceptionally well. And in this case, that one thing was the very specific kind of math that powers neural networks. They called it the Tensor Processing Unit, or, as you've probably heard, the TPU. Okay, so to really get what makes the TPU so special, you have to see how different it is. A standard CPU, the kind in your laptop, is what we call a scalar processor. It does one thing at a time, kind of like typing one single letter. A GPU is a vector processor. It's way more parallel, it can handle thousands of things at once, like printing a whole line of text. But the TPU, it's a matrix processor. It's designed to process hundreds of thousands of operations all at the same time. Forget printing a line, this thing prints the entire page in one go. The real magic trick inside the TPU is this thing called a systolic array. Just picture a massive grid of over 65,000 tiny, simple calculators. Now, instead of each one having to go all the way to the chip's memory to grab data, which is super slow, they just pass results directly to their neighbors. Data flows through this grid in these coordinated waves, almost like a heart pumping blood. This simple-sounding idea slashes the time and energy wasted on accessing memory, which is one of the biggest bottlenecks in any computer chip. And get this, they pulled this off at a completely breakneck pace. This quote from Norm Jupe, the project's tech lead, really paints a picture of the urgency. They designed the chip, built it, and got it working inside their data centers in just 15 months. I mean, that is just unheard of for a brand new processor architecture, especially when you're still hiring the team to build it. Hectic is probably an understatement. So, was it worth it? Oh, yeah. The results were just staggering. The very first TPU delivered between 30 and 80 times more performance for every watt of power used compared to the CPUs and GPUs of that era. This wasn't just a small step up, it was a gigantic leap. This was the breakthrough that solved that impossible data center problem. But the story doesn't end with a new piece of hardware, not even close. The next huge performance boost came from the software side of things, from a clever technique that started with a really simple question. For AI, how much precision do you actually need? And this is the perfect way to think about it. This idea is the key to a technique called quantization. Basically, it recognizes that for a lot of AI tasks, you don't need perfectly precise numbers. You just need a good enough answer. And if you can use smaller, simpler numbers to represent your data, you can do your calculations way faster and with a lot less energy, as long as you don't make your AI model any less smart. So in computing, the size of the numbers you use determines their precision. AI models are usually trained with these very precise 16-bit numbers, but the real speed demon is the simpler 8-bit number. It's half the size, so it's much, much faster to work with. But that was the million-dollar question, right? Could you actually switch to these simpler numbers without hurting the AI's performance? So engineers tried a few things. The first idea was to train the AI like normal, and then just switch to the simpler numbers at the very end. But that often messed with the model's quality. A better way was to make the model aware of these simpler numbers while it was training. That worked great for making the AI run faster once it was trained, but the real holy grail was figuring out how to use these fast, simple numbers to speed up the training process itself, which is the most expensive part. For a long, long time, speeding up the entire training process this way was mostly just theory. You'd see it in research papers, but actually making it work in a real-world production environment, that was incredibly complicated. That is, until a new software library came along and changed everything. The breakthrough was a library called Accurate Quantized Training, or AQT. It's open source, And it basically handled all that mind-bending complexity for you. It finally let developers use these super advanced techniques on huge AI models without having to be world-class experts in quantization themselves. And the results? They were just incredible. When AQT was used to train the massive GPT-3 model with those simpler 8-bit numbers, it clocked in a 139% speed up. Think about that. The training was nearly 1.5 times faster. Okay, so it's way faster, but what's the catch? What about the quality? Well, this is the best part. The trade-off was basically nothing. The difference in the final model's accuracy was less than 0.1%, an almost indistinguishable difference. Getting a massive speedup with virtually zero quality loss, that is a huge win. And this all brings us to the real key takeaway. The fastest chip in the world is only as good as the software that can actually take advantage of it. The TPU's hardware and AQT's software, they aren't two separate things. They're two sides of the same coin. And this is the future of computing. It's co-design, where hardware and software are built together in perfect sync to achieve things neither could do alone. Now, the TPU and AQT don't exist in a vacuum. They're just two pieces of a much bigger puzzle, a whole open-source ecosystem called the JAX AI stack. You can see it here. It's a set of modular tools, each designed to do one job really, really well. From the core math in JAX to building models in Flax, and of course, quantizing them with AQT. It lets developers basically assemble the perfect high-performance toolkit for whatever AI problem they're trying to solve. Ultimately, the TPU's power comes from its relentless focus. This quote really says it all. Minimalism is its virtue. By stripping away all the complicated stuff a normal chip needs to do everything okay, and focusing only on the matrix math that's essential for AI, it achieves this unbelievable efficiency. It's proof that sometimes doing one thing perfectly is way better than doing everything just pretty well. So the story of the TPU shows us this amazing cycle, right? The incredible demands of AI drive new hardware. That new hardware unlocks new software tricks, which then pushes AI even further. And it all leaves us with this one fascinating question. As our AI models keep getting bigger and more complex, what's the next impossible problem that will force us to reinvent the computer all over again?